Okay, now I would like to share you the relation between the continuity equation and the volume flow rate actually. Okay, Assalamualaikum dan salam sejahtera. So for today, I would like to introduce you about the stream function. So stream function in this chapter, okay, is written by this symbol. So it's called as psi. So means that if we call psi, so you could write like this one. So this is psi. Okay. So psi is called as stream function. Okay. So what is stream function? So stream function is actually a volume flow rate. So means that previously in fluid mechanics 1, we know that flow rate is Q equal AV because we are evaluating the incompressible. Okay, so incompressible. Okay, and then we are only evaluating in 2D. Okay, and then but in ideal flow, we could say that because previously we are evaluating velocity. As you remember in chapter 1 in a differential method, our aim purpose is to get the velocity distribution for from the Navier-Stokes equation. So and then means that we will use the velocity to derive our stream function. Means we do some kind of reverse engineering calculation. First, we evaluate or we determine the velocity, then we could get the flow rate. Okay, why? Because in real experiment, for example, sometimes we measure the velocity of flow, and then we multiply with the cross-sectional area, then we could get the flow rate. Okay, so but in ideal flow, in these topics in chapter 2, we are not using volume flow rate per se. We are using stream function. So means that now you just remember that a stream function, okay, is actually carries the same meaning of volume flow rate. So if we have velocity, it means if we have volume flow rate, we could divide it by cross-sectional area and we could get the value of velocity. So means I hope you could understand this equation because it is already learned in fluid mechanics 1. Okay, so now I want to show you how we could relate the stream function and with the velocity. So let's say this is the Cartesian coordinate. So let's say we have a molecule like this one, a square like this one. So and then we assume that the distance for x here is dx and the distance for y here is dy. And we assume that the width of this box is equal to 1 unit. So means that if we want to relate the stream function and the velocity, we could write as this one. Means that we know that Q is equal to AV, and then we could write velocity is equal to Q over A. And then, so in this situation, we say that volume flow rate is actually written with psi symbol. So V here is equal to psi over A. So however, we don't use the absolute V like this one. So because we have a small v, a small u, and a small v here, so we could write as this one. So u here is the velocity in x direction like this one. And to calculate the u velocity here, we could do by dividing d psi over dy. Means that this d psi here is the stream function according to x-axis here, and dy here is the cross-sectional area, the A. Okay, why we use dy? Because this is the height of this box. Okay, this is the height of this box, and we assume that the width of this box is equal to 1. So mean the A here, okay, the A here is dy times 1. So it's remain as dy. So means that to have the u here, we could get by d psi over dy. And what is the meaning of d here? D psi and dy. So the meaning of d here is actually because we assume that this diagram is reflecting or represent the small portion of a fluid flow. So a small portion, so we could show as dy and also d psi. Okay, I hope you could understand why we use d psi over dy, because we are evaluating a small portion in a fluid flow. Okay, and then if we write the relation between psi and v, okay, so this is v, and then we know it's a flow from bottom to the top like this one, upward. So we could say that v is equal to d psi over dx. And again, this is the distance of this side dx, and we multiply with it with, which is 1. So w is equal to 1 unit. So it remains as dx. Okay. However, in this situation, okay, you need to add a negative sign here. So this is a compulsory. Why? Because after this, we will evaluating stream function in polar coordinates. So in polar coordinates, okay, we need to differentiate between the counterclockwise rotation and clockwise rotation. So means that, and then for certain operation, we need to merge between Cartesian coordinate and polar coordinate to make sure that our calculation is correct. Means that we need to give another direction. The means positive and negative in terms of clockwise and counterclockwise. So in this situation, okay, so in your syllabus, we agree that we give the negative sign for counterclockwise. So means that because if the velocity is moving upward like this, so means that if this molecule is nailed at one center point here, so means that this molecule has tendency to rotate in counterclockwise. So because it has tendency to rotate in counterclockwise, so we put a negative sign in these terms. Because if you realize flow rate is actually a scale, a scalar. So means scalar means you don't have to put negative or negative. That's why in fluid mechanics 1, for example, if you had tank here and you have a pipe, whether it is upward like this or whether it is downward like this, or if it's flow backward like this one, so the flow rate here will always positive, because volume flow rate is only need to be calculated as a magnitude. So the direction of flow rate or volume flow rate is not counted. So it is different with the velocity. So velocity is a vector. So you need to know what is the magnitude of your velocity and also what is the magnitude and what is the direction of your velocity. Okay, so this is the relationship between the stream function and velocity for the Cartesian coordinate. And this is the relationship of stream function in polar coordinate. So I think, I hope you could draw this diagram. So we already show you this diagram a few times. So, and then this is the velocity. okay, parallel with the theta axis. So we write as u theta, and this is the ur, the velocity which is parallel, or velocity on the radial direction. And the distance here is dr, and the distance here is r d theta. So I hope you're familiar with the diagram, and you could draw by yourself. And then we could write the ur here as d psi over r d theta. I think the explanation here, you already know why we could write like this one, because this is ur, and then okay, we could have the value of ur by dividing the stream function with the cross-sectional area. So the cross-sectional area here is an area which is perpendicular to the velocity. So this is the r d theta, and then we multiply with the thickness w here is equivalent to 1 unit. So we have d psi over r d theta. And for u theta here, so we have negative d psi over dr. So this is the value, the velocity of u theta, and then we divide with the cross-sectional area here. So this is dr, as stated here. So and then dr, and then the width here is w is equal to 1. So it's remained as d psi over dr. And again, because the motion here is the counterclockwise, so we put a negative sign in this equation. So I hope you could remember these two situations, and I hope you make no mistakes to evaluate the to write the stream function and the velocity component. So we have Cartesian coordinate, and we have polar coordinate. Okay, so what is actually stream function or streamline? Okay, so streamline, as I say, is actually the volume flow rate. So streamline is actually measurable. So and means that it can be proved in experimental work. So one of the simple example of stream function or streamline is the smoke line in wind tunnel. Okay, it will create something like this. So I think you could imagine that a wind tunnel means we have a tunnel, whether it is small or big tunnel, and then you will put your object here. So in this situation, so we have a car here. Okay, so and then we will provide them a smoke. So the smoke is come from the smoke generator. Okay, you may Google about this one, and the smoke will flow between the molecule of air, and it will visible like this one. Okay, so this is a streamline. Okay, so that's why if you read about a sport car, they will say that a streamline design and so on and so forth, because it shows that the design of that car will give you a curved line, a very smooth movement. So because if let's say if you have a box, a square object here, so the streamline will need to move like this. So if the streamline is moved in a very wide angle, so means that the resistance of that flow is high. So means that to release the to reduce the force, to reduce the resistance occur from this object, so we need to streamline the shape. Okay, so that's why in our calculation, we start our calculation by using the idea of psi, or stream function, or volume flow rate, because it is important for us to make sure that our calculation is correct or verified, or can be verified from the experimental work. Okay, that's why we start with the stream function, because stream function can be evaluated in experimental work. We could compare between experimental work and with the calculation. Okay, so what is the usage of this evaluation? So first, we could create we could know the resistance. So the resistance is actually will lead us to drag force, and then or a lift force. Okay, we will continue to learn about this in chapter 3. Okay, so we could calculate the lift force, we could calculate the drag force, we could see the vortex here. So the word vortex here, so vortex mean the rotational of flow behind the car. Sometime in certain textbook they will give you about wake, so it is actually the same things with different names. Okay, so it will give us information about this one. And because all of this motion is represent in mathematical terms, so means that it is useful when we want to do this in simulation way. So another thing that we could have with the stream function is we could know about the aerofoil like this one. Okay, we could determine how smooth the wind flow, and then the pressure difference between the bottom part and the upper part here. Why? Because in aerofoil here, they will create lift force. Because the basic idea is if the velocity is higher at the top here, so mean the pressure is lower. So means that if the velocity at the bottom here is higher, is lower, so means that the pressure is higher. So means the pressure difference here will give us lift force. So we are purposely create the aerofoil here to give us different region of velocity. That's why normally we hope that the pressure at the bottom here is greater compared with the pressure at the top here. So means that the total force will go up there. So the upward force here is called a lift force. So this is the basic idea how to fly an aeroplane. Okay, you could watch YouTube by using this link, okay, or you could search by yourself in YouTube. Okay, so everything is at your fingertips. Okay, so we stop here. Okay, now I would like to introduce you another term which is called the velocity potential. So the velocity potential is actually the imaginary line. Okay, so this imaginary line must perpendicular to the stream function. So what is the purpose of this one? Okay, so the purpose of this one is, so from the experiment and from our calculation of stream function, okay, we could have all this line. Okay, we could draw this line. Okay, however, this calculation of this line is not enough for us to simulate the situation or to calculate the lift force, drag force, and other parameters, because it is not easy when we only have a horizontal line. So in grid, okay, it is good for you to have X and Y, means you know the location of horizontal and at the same time you know the location of vertical line. So same like this one. So in general term, we could say that the calculation is cannot be made because we only have a horizontal line here. What we must have is we need to draw a vertical line along this one. Okay. So this vertical line is actually cannot be represented or cannot be proved in experimental work in real life, because this line, this horizontal line is our imaginary. So our imaginary to help us, to ease us in calculation, in our calculation. That's why, and we have formula to do this, okay, and it is known as velocity potential. So again, you must know that velocity potential here is the imaginary line which is perpendicular to the stream function. So it must be perpendicular to stream function. Okay, so before we go to velocity potential, I would like to introduce you one parameter called circulation. Okay, because previously in Cartesian coordinate, we are using continuity equation. So mean because we have a one object here or one, and then flow will comes in and comes out. So we are talking about the total flow rate, inlet and outlet. But in other application, maybe we have a motion or movement of fluid which is rotate in circular shape, in circular motion. So we call this one as the circulation. So what is the idea of circulation is, okay, so circulation for a closed contour is a fluid. In a fluid is defined as the line integral evaluated along the contour of the component of the velocity that is locally tangent to the contour. Okay, in easy words, we could say as, so this is, circulation is the total push you get when going along a path such as a circle. So for example, you have a one molecule here and molecule here is complete its circle like this one. Mean circulation mean actually the total power, the total force needed by this. It's actually not force, uh, it's something like force. I mean the total push of this molecule to move from this starting point to its ending point, which is the same location. Okay, so and then we need to determine what is the equation that could reflect the circulation. So the equation to represent the circulation can be written like this. So circulation is written as gamma. So this is the capital gamma. You could write like this one. You start with this uh, straight line, and then you will have one symbol like this one. So this is the gamma. And velocity potential, the definition is the multiply of the velocity component with the total area of the motion. Okay, the idea is ialah gamma ialah circulation. Membawa maksud adalah hasil darab velocity component. So kita ada, let's say we have U here. Hasil darab U dengan total area yang dilalui oleh sesuatu molekul. So kenapa kita kata total area? Tetapi kenapa kita hanya darab dl? Okay, kerana kita beranggapan bahawa width of this path is equal to 1 unit. Okay, so kita kata width di sini kita anggap sama dengan 1 unit. Okay. So jadi saya harap awak boleh faham rumus ini. Okay, yang paling mudah awak hafallah rumus ini. Tetapi kalau awak ingin tahu kenapa, dari mana ia dibuat, antara yang mudah ialah ia berentetan daripada idea Buckingham Pi Theorem dan similarity. Okay. Kita tahu bahawa psi adalah U yang didarabkan dengan L. Kerana kita beranggapan adalah A sama juga dengan L darab W. So maknanya W equal to 1. So jadi kita A is equal to L. So this is a stream function. So for okay, sorry. Yang ni nanti saya terangkan akhir ni. Awak tak masuk lagi perkataan phi ni. Okay, so it's okay. So saya ulang lagi sekali di sini. Okay, jadi first what you need to understand is about the circulation. Okay, the circulation is, the idea is, it's written by gamma, and the equation is the multiple of u component velocity with the distance traveled by the fluid. Okay. So and then circulation here, okay, will change according to the area. Okay, yang di sini yang awak kena faham, because the equation of circulation, we have a distance traveled by the fluid. So means the longer the distance means the higher the value of gamma. And this make this circulation cannot be used to compare with one and other molecule. Okay, selalunya kita kata rumus ini kita kata kurang cekap untuk kita gunakan untuk membandingkan antara satu pergerakan dengan satu pergerakan yang lain, kerana ia mudah untuk mengelirukan kita lah, mengelirukan kita. So contoh yang paling mudah berkenaan dengan ini ialah contohnya kereta. Okay. Ada sebuah kereta 1800 cc berat katakan 600 kg dan menghasilkan berapa, katakan 250 horsepower. Ada satu kereta 2000 cc berat, mungkin berat sedikit 600 atau 700 kg, menghasilkan lebih besar sedikit horsepower. Jadi di sini sebenarnya kalau awak rajin membaca berkenaan dengan kereta dan sebagainya, selalunya pakar-pakar kereta ataupun pengulas-pengulas kereta, mereka tidak akan terus membandingkan nilai horsepower yang ada pada dua kereta ini. Kerana secara normalnya ataupun secara kelazimannya, semakin besar cc tersebut, semakin tinggi horsepower. Jadi tentulah yang 2000 cc akan menang. Tetapi pengulas kereta selalunya dia akan menggunakan, kita kata, horsepower over weight ratio. Maksudnya walaupun horsepower dia tinggi, tetapi ia perlu melawan berat badan kereta. Oleh itu nilai horsepower dibahagikan dengan berat badan kereta, kita boleh dapat satu ratio. Dan ratio itulah yang digunakan untuk membandingkan performance antara dua kereta. Barulah kita kata perbandingan itu dapat dilakukan dengan sempurna, kerana kita telah mengabaikan luas atau berat yang ada pada kereta tersebut. Okay, sama juga di dalam kes ini, okay, in this situation, because in this equation we have area here. Okay, we have area here, so means that the bigger the area means the higher the value of gamma. However, we cannot determine whether that gamma is actually the push, means the total force feel by that molecule is actually how much. We cannot determine that. So that's why we determine, or we introduce you another term which is called the vorticity. So the vorticity is written in gamma as zeta here. So you could write like this one. Okay. So if you cannot write this symbol, it is okay for you to write as a Z. So even in textbook, they will give you a different symbol here. Okay, because gamma is zeta, sometimes it is not easy to write in handwritten answer script. So it is okay for you to write as Z. So what is the definition of vorticity? So we define it as the circulation divided by the area. So it is to help people to have a fair comparison about the vorticity and circulation. Okay, so in other words, is vorticity is the tendency for element of the fluid to spin. Okay, so maksudnya tadi kita telah melihat circulation U times dl. So and then this is telling you about the whole force, the whole power that occur when molecule completely rotates and come back into its original position. And the vorticity here will show you actually what is the tendency of the fluid. Means the tendency of that one molecule to spin. Okay. Okay, how to calculate this one? Okay, let's say we have a Cartesian coordinate like this one. So from where we could write this one, so you just imagine that we have a lot of molecule here. So and then, okay, this is, we have another streamline with another molecule here. And then again, we have a lot of molecule here. We just imagine we have this one. And then the U means the possibility of this molecule to move in X direction. And V here is the possibility of this molecule to move at a Y direction, in Y direction. So, and then we assume that the velocity at this point, okay, and velocity at this point is different. Also, the velocity at this point also different, and so on and so forth. Okay, and again, the V velocity here, okay, is different with V velocity here, and different with here, and different with here. Okay, it is just to make sure that our calculation is very unique. So it means that we have the, so to show the difference, we write as V and V plus dV. So we have U here, and then we have U plus du. If, okay, if the velocity is equal to this here, to here, so the value of du here is equal to 0. That's it. Okay. Okay. Now we calculate the gamma. Okay, this is the gamma. And you must know that the gamma is, the basic idea is gamma U times L. So which is L here is the distance traveled by the fluid. So and then this calculation is about the rotation. So we assume that if this molecule move here and then move upwards, move to the left, and then again go back to its original position, so means that this molecule can be assumed it's already moved in circulation, in circle motion. Okay, so here we could calculate its gamma, its circulation. So the idea is velocity times distance. So for this times, for this side, so we could write as u times dx, because we have a positive u and the distance here is dx, mean the distance on x-axis. And then for here, the velocity is going upward, so we have v plus dv times dy, because dy here is the distance traveled by the fluid. And then for this one, for this motion, so we could write it is as negative. So I think you already know. So because we assume that in positive way, the velocity is u plus du, but if we move reverse direction like this one, so it will become negative u plus du times dx. And here it's move downward like this one. So and then we give it as negative v dy. So if we calculate this one, we could have these terms. So after you expand it, you cancel it, and then you could find that gamma is dv dy minus du dx. Okay, so and then if we want to calculate the vorticity here, the zeta here, so we take the value of circulation and we divide into with A, the area. So what is the A? So we could assume that A here is actually the area of this one. So the area of this one is dx times dy. So if we solve this equation, we could find that zeta is equal to dv over dx minus du over dy. Okay, so and then I would like to show you how to calculate, how to derive the circulation and vorticity in polar coordinates. So this is the diagram that you should know to represent the molecule in polar coordinates. So it is the same. So we have a lot of molecule here in certain line like this one. So this is the origin. So we assume that it has velocity of u theta at this direction, and this is the velocity which is on the radius area. The radius exists, so which is the ur. Say the distance here is dr, and the distance here is r d theta. So I hope you could imagine the of this diagram. So and then we know that the gamma is u times u equal gamma is u times distance traveled by the fluid. So we start from here. So this is ur times dr. So and then it's moved here. So it's become u theta plus du theta, and r plus dr d theta. I hope you could imagine because we have r here. So here is dr, and that's why we have r and dr, r plus dr d theta. So d theta is here. Okay, and then for this one, because this is the negative direction, okay, so we have a negative term, and then here again the negative term, so it has negative u theta r d theta. And if we solve this one, we could get this term. So this is the circulation in polar coordinate. So and then to calculate the zeta, so we use the same idea, which is the circulation divided by the area. So this is the circulation that we calculated previously, and it is okay for us just to simplify our calculation of area here by r dr r d theta. So r d theta mean the distance of this side, and dr mean the distance of this side. Just we assume that the area here is very, very small, so we could say that it is okay, it is acceptable for us to calculate the value of area here is dr times r d theta. And then if we solve this equation, so we could get these terms, and this is the final term for the vorticity or in polar coordinates. So I hope you could derive your own continuity equation and followed by the stream function, and then here you could calculate the vorticity. And okay, I would like to after this we will go for velocity potential. Okay, so what is the meaning of vorticity here? Okay, so the meaning of vorticity here is like this one. First thing that you should know is in continuity equation, okay, in continuity equation, okay, you must always get 0. Okay, awak kena ingat bahawa di dalam continuity, kita kena pastikan bahawa nilai continuity akan sama dengan kosong. Kerana ini bermaksud flow in sama dengan flow out. Okay. Tetapi vorticity is not always equal to 0. So vorticity means can be equal to 0 and can be not equal to 0. So it can be, normally we took as a positive value. So if the zeta is equal to 0, we call it is an irrotational flow. If zeta is 0, mean it doesn't has any tendency to spin, so mean it's irrotational flow, not rotate flow, not so we call it irrotational flow. Then if zeta is not equal to 0, means zeta has certain value, mean that molecule has tendency, has inner power to spin, so we call it as a rotational flow. So please remember these terms. Okay. So however, after this, we will do our analysis, our calculation based on ideal flow. I will introduce you a lot of equation after this. And all of that equation is actually only suitable with the irrotational flow only. Okay, because for rotational flow, we need to add an internal force actually to assume that the molecule will can be rotate. Okay, so please remember this: if zeta is equal to zero, it is irrotational flow. If zeta is not equal to zero, it is rotational flow. Okay, what is the idea of rotational and irrotational flow? You could see like this one. So this is the velocity distribution. So I think you know that in reality, molecule on the surface here will stick very hard, and the velocity is equal to zero. So it is called the no slip condition. So I think in fluid mechanics 1, you already learned about this so much. Okay. So and then the velocity will increase and increase, and after at certain point the velocity will remain constant because it already reached the steady state condition. Okay. So and then because in this region, okay, why we assume that molecule is actually could spin itself? Because they are different of resistance. So means that you know why this area we have different of velocity profile, because for example we have 3 molecule here, so the resistance at the bottom molecule here is not equal with the middle molecule, and not also not equal with the upper molecule here. That's why because that's the reason why the velocity distribution here is different, because the shear stress is not equal. So that's why because the forces here, the interact forces here is not equal between top and the bottom one, so means that this molecule actually has tendency to rotate. So this is the basic idea why we normally assume that in velocity profile like this one, the region that has a different in velocity profile, we assume that the molecule has tendency to spin. So here we call it as a rotational flow. Okay, and then in chapter 3, we will learn about the boundary layer region. So normally in boundary layer region, so the flow is rotational flow. So for this area, because we assume that the fluid here flow in same velocity, so means that the interaction between upper molecule here and the lower molecule here is actually the same. That's create the molecule move at same speed. So means that it's neglect the tendency to the for the molecule here to spin. So that's why we call it that it is the irrotational flow. So I hope you could understand this one, the idea of rotational and irrotational. And for in ideal flow calculation, we assume that all our condition is irrotational flow. Now, we would like to introduce you about the velocity potential. So the velocity potential is written as phi. So we call it as phi. PHI is phi and PI is pi. Okay, please be careful. Okay, pi, PI, and PHI is phi. So the sound is FI, phi. Okay. Okay, but we not write as FI, so we write as PHI. So the sound is phi. So it is phi. So and then phi here is actually the velocity, the U times the distance traveled by the fluid. So if you see here, the definition of this one is actually similar with the vorticity of the circulation. So velocity times the distance traveled by the fluid. So if you look back into the previous notes, you will find that the stream function is U times L, which is L is the cross-sectional area. So, and then it is equal to Q. And then the phi here is equal U times L again, but the L here is actually the distance traveled by the fluid. Okay, so in this situation, so as I said, the simple assumption for this one is they propose this equation by using the similarity. You know that the similarity that you learn in fluid mechanics 1, you have a Buckingham pi theorem and so on and so forth. So we assume that the velocity parameter here is not easy to change because it represents the way fluid molecule move. But the only way to change is to change the geometrical parts. So here is the cross-sectional area, and we change this term with this travel by the fluid. Why? We take the travel of the fluid because in velocity potential, we are aiming to evaluate a rotational movement. So the rotational movement here is actually, it is more dominant. It is more influenced by the travel distance instead of cross-sectional area. Okay, that's the simple reason the development of this equation. So I hope you could understand that. But the most important is for you to remember this equation. So phi here is the velocity times the distance traveled by the fluid. So if you change the arrangement of this one, we could have U is equal to phi divided by L. So, and then if we see the Cartesian coordinate, we will do the same, a simple evaluation. So for U here, we could write as d phi over dx because dx here is the distance traveled by the fluid. So we imagine that this is the velocity. So this is the distance traveled by the fluid. And the v here is d phi over dy. So means this is the direction of v. So this is the distance traveled by the fluid. So we have d phi over dy. So, and then in this situation, there are no negative or positive sign because this is not reflecting the real situation. This is an imaginary line. And for polar coordinates, again, so we will we use the same diagram like this one, and then we could write UR is equal d phi over dr because, okay, this is the direction, and dr here is the distance traveled by this flow. And u theta is equal to d phi over r d theta because, so if this is the direction of travel, so this is the distance traveled by this molecule. So it's become r d theta. Okay, so I hope you could understand this because this is a very simple assumption. So, and then what is streamline and what is velocity potential line? As I said, so the streamline actually is the flow rate here. Flow rate at every location. And then the potential line is actually the perpendicular line, which is the imaginary line to help us in calculation. So, okay, this is another idea. So there's the psi here. So the psi here actually showing you the real flow. But the tangential line here is the phi is actually an imaginary line to help us in our calculation. Later on, I will show you. Okay, so you could see this one, and this is another example. We will have this kind of calculation. Okay, okay. So finally, if you see all my notes here, okay, we have Cartesian coordinates and we have polar coordinates, and then we have psi and we have phi, and then all of this equation is merged, okay, as known as Cauchy Riemann equation. So Cauchy Riemann equation is actually the idea from Augustine Cauchy and Bernard Riemann. Okay, so the most important things here is you need to remember Cauchy Riemann equation. So this is very important because all the derivation is actually based on this equation. So we have u equal d psi over dy equal d phi over dx, and v here is negative d psi over dx equal d phi over dy. And polar coordinate is showing like this one. Okay, and please bear in mind that the negative only occur at this equation only. So negatif tu hanya berada pada negatif d psi dx dan negatif d psi dr sahaja.